Welcome to the CircuitPython show. I'm your host, Paul Cutler. This episode I'm joined by Michelle Hui and Reitwiec Shandilya. Michelle is a master's student at Cornell Tech in AI and urban technology. Her practice includes accessible technology for good across health and climate. Previously, she has worked at Wing, Google's drone delivery moonshot, and the United Nations. Reitwiec is a master's student at Cornell Tech and a fellow at 645 Ventures, where he focuses on early-stage investments in AI infrastructure, security, and hardware. Previously, he was an early member of SAP's AI team, working on enterprise AI solutions. Michelle and Reitwiec, welcome to the show.
Thank you for having us. So excited to be on.
Yeah, super excited, Paul.
You've worked together to develop the Open Pressure Sensor Device, or OpenPSD. What is the OpenPSD?
So the OpenPSD, we began working with Weill Cornell near Presbyterian. But after, female patients have cancer, specifically breast cancer, and they get mastectomy, it leads to serious loss of quality of life because they often say that their chest feels like it doesn't belong to themselves anymore. When they hug their children, they can't feel their children. So there's this surgeon at Weill doing super cutting edge research where he essentially can reconnect your nerves and help you regain sensation in your chest. But they had been using this proprietary medical device, and the private company decided that it was no longer profitable anymore, and they essentially abandoned the device. And not just this surgeon, but essentially all the research labs across the US doing any sort of nerve sensation, whether that's diabetes and you lose sensation in your foot or your fingers, essentially lost access to this one device. So what we did was we actually engineered that from black box, and we rebuilt this pressure sensor device, hence the name OpenPSD, Open Pressure Sensor Device.
But yeah, our goal with this was essentially to quantify sensation and nerve function and help expand it to other clinical and neurological settings, as Michelle said.
What were some of the problem gaps that you were trying to resolve in addition to that?
I think beyond just this proprietary medical device, before that, they literally used to use one monofilament, and you would just use a filament to poke at various areas of your skin. So it's this super outdated, archaic method. And so our open source device isn't just replacing an abandoned medical device, but it's actually innovating on this super archaic nerve sensation method. And on top of that, we're also working with OSHWA, the Open Source Hardware Association, to explore what happens to any medical device when expensive med tech decides that it's just not profitable to maintain anymore. How can we democratize healthcare medical devices? How can we make a framework for open source, but also reliable? And so those were the two, I think, larger impacts that we were trying to address through the project.
How did you collaborate with clinicians during the design process?
Something that we discovered when we saw the proprietary device was that it had been completely over-engineered. It had been super expensive. They came with this giant briefcase, almost Matrix style, supervillain style briefcase. And they pulled out like a proprietary tablet, almost their own iPad, and it had their software installed. And then they had this giant acquisition unit. And then they had this the super boxy handheld device. And we just felt like it had been so over-engineered. And we could tell that they're probably trying to upsell it, have software maintenance. And so we came in and we asked them even on the first day, like, if you could get rid of all of this, what would you want to get rid of, right? And we were able to change all of that giant briefcase into literally the size of a screwdriver. And that's all you needed. It was a screwdriver, and it was, software that you could install on your own MacBook. And so we were working with clinicians every single couple of weeks. They would come back and they give us feedback. I remember one time the surgeon came in and he felt our device and he's like, your wires that are doing the sensing need to adjust because it's actually hitting other areas in the skin. And it was just something we had totally, not thought about, and we didn't understand how they were using it at all. And so I think what we're able to do in open source and what we discovered is that because open source isn't meant to make money, you don't have to try to start upselling everyone, and you don't have to create this black box med tech industry. We can actually go back and forth with the clinicians and really improve and do exactly participatory design and create a participatory framework to improve clinician efficiency and just improve the workflow overall.
And something really exciting here was that, I don't know, we hadn't really thought about before was the initial device that they came up with was, it looks really daunting as well. I think as a patient, you're in a very vulnerable state when you're going through this entire process. So imagine someone coming in with a huge briefcase and takes out this huge gigantic tech device, it's really, really, really unnerving sometimes. And so our whole goal there as well was we want to make patients feel safe. We want them to trust our device. Yeah, and I think since it has gone into the clinic, we're still waiting for the PI's feedback, but we're looking forward to that.
You mentioned that you got it down to the size of a screw. Tell me a little bit more about the hardware, and then tell me what role CircuitPython played in the development of the firmware.
CircuitPython was our firmware, and the idea, the way it was built was we had a load cell, and we have filaments attached to it, and we had sort of custom wired and custom twisted this filament at the end of the load cell. And this load cell then had a sensor, a pressure sensor, which is attached to the load cell, which then goes to our firmware where we process these signals. And we had some custom logic just for getting, let's say, set ton of values, taking an average out of it. And whenever someone presses the button, it calculates that pressure that's being applied to the load cell. And from there, we display on a UI that we had created, which is running locally as well, because we didn't want to keep it on cloud because it was personal patient data as well. But yeah, that's how the overall device was set up in terms of hardware.
What kind of screen was the UI displayed upon?
It was just a laptop. It was it was just coded up in React, and I think so. The other goal that we wanted to see with this project was how quickly can we iterate and get feedback. And surprisingly, AI did play a pretty good role there, and it helped accelerate quite a bit of our stuff. And since going into it, I did not know a lot about, let's say, how load cells work or just the tech behind it. Because when we were reverse engineering stuff, we came across these small parts which we hadn't really seen before. So I think doing the initial research and getting some relevant information and then helping with some initial setup, because our main goal was to focus more on the device itself. And like the secondary things that came up with it were, let's say, the UI or whatever else. And so we weren't completely focused on the hardware. And AI helped in finishing up the secondary task here really quickly, and we were able to iterate really quickly. We got the PI to the lab, and we were just helping him go through the interface, and then we got some feedback here that this can be here, this can be done this. That was pretty exciting, yeah.
So did the AI help with writing the actual CircuitPython code that you used on the device?
It was a mix, honestly. So initially, it was just going through all the different documentation that we could find online for. So let's say our sensor was HX 711. So figuring out information for that. The initial boilerplate code was provided by AI. That was pretty helpful, and then just fixing it by bit, piece by piece, was more of our own experience and just our own software experience. Yeah.
You mentioned a couple minutes ago that you had to reverse engineer the proprietary device. How did that process go?
That was interesting. So the device was like this. Imagine a square Mac Mini style, but small Mac Mini style device. And so it was just a lot of unscrewing stuff, taking it all apart. And then when we opened it, there were these small, small cables inside and these small, tiny load cells. And we were like, okay, this seems interesting. Then the next part was we had to balance between buying stuff that's already out there and making use of that and making our own custom things. Because the whole point of open source was that, hey, if you're going to build something from scratch, we want it to be accessible. Like, for example, let's say if we were to go ahead and build our own load cell, then for someone to build it and replicate it, it's going to be really hard. So we decided we go on Adafruit, we find a relevant load cell, and then we design around that. So that was another key thing that we had to keep in mind. Then, as we were exploring, we were trying to see what materials were used, because the filament that's used to poke on the skin needs to be flexible enough, but it also needs to be rigid. So we tried experimenting with different materials, and then eventually, I think we resulted with an aluminum kind of thing, right? If I'm not wrong.
Yeah, to add on to that, I think one of the challenges, the overarching challenges to everything Reitwiec described, was we didn't know what was good enough, especially because it was medical quality, right? I think if it was another open source device for tinkering or a watch, I think you can get away with a lot looser things. You can get away with different parts. But we were always like, is this good enough? Is this accurate enough for medical application? And the Mac Mini device that came to us, as Reitwiec mentioned, like we had started hacking it apart because we didn't know how it worked. Like we literally took a saw and cut out pieces of the aluminum, and then we like pulled off the prongs and we started using it ourselves. But it was broken. So we truly had no idea how it was measuring and how accurate it was. And so when we were building our stuff, we almost hit like a 2-month delay or like stuck point because we were just not really sure where to proceed. We were like, we don't want to build our own custom load cell. We want to use what's off the shelf, but we don't know if this load cell is good enough. For example, our load cell, I think in a range of up to, I think 1 kg or 10 kg, if I'm not mistaken, but we only needed a tenth of that. We literally only needed 1 to 100 grams of measurement force. And so we're like, if we're only using such a minimal part of its range, is there too much noise? Are we able to detect it? And so we truly had no clue how to reference it. And then another issue we faced with reverse engineering from black box, we thought the whole time that it was measured in this measurement called like grams force over area to get pressure, if that makes sense. So, the tip of the wire is like a diameter of like 1 millimeter. And so we're like, oh, we have to calculate the pressure and then calculate the force and divide it by the area to get pressure or whatever. And so we're going through this complicated, convoluted conversion. And then the clinician comes back and he pulls out the real functioning device. And we realized they didn't do any of that. We realized they were literally just converting directly to force and just doing it and just reading out that measurement. And we actually felt totally lied to because all the papers had said that it was over area. And I was like, wow, no one actually even knows how this device is working. And they just had some arbitrary readout. And we found out that our device was almost almost just as accurate, if not more accurate than their current device, and was able to read forces better. It was able to read closer to 0 as well. And so I think that was one of the big challenges we faced, was just validating against medical accuracy and having medical standards. And this is important because, as we're trying to build a framework for all of the open source devices out there, especially medical devices, I think this is a challenge that everyone will face. How can we validate with the scrappiness of open source, but also make it reliable and production grade for the medical industry?
Yeah, and I think like something else that so stood out for me was while we were going through this process, as we did this, as they call it, contextual inquiry, we were looking at the PI, do they use the device proper on its own, and then I think there was a part where you had to ask important questions, like especially when it comes to accuracy, right? Something that we realized was because the device is measuring the sensation over a period of time, we wanted to know what our tolerance was for accuracy. Because at the end of the day, fundamentally, we were seeing whether the sensation is improving. So even if, let's say, they were let's say a 1%, 2% error, it would have been sort of acceptable because in this particular situation, the main fundamental use for the device is to see like an overall growth over time. So I think the important part was asking important questions like, hey, what's the real use for it? Just because it needs to be done this way doesn't really mean that it has to be done that way. So I think when it comes to open source medical hardware, it's important to understand what your tolerances are, acceptances are. And the second part was these guys are really busy. So we had to really plan. One of our first calls with the surgeon was he literally stepped out of the OR just to talk to us for like 5 minutes, and it was insane. So I think that the second point was we had to plan it out properly, and it was interesting.
So you've been talking a lot about open source. Will you be certifying the OpenPSD with the Open Source Hardware Association?
So we did talk to our point of contact with OSHA, and he did say that I think OSHA would be really, really happy to help us certify. They would also want to do some sort of blog about us and just sort of help us reach out to as many people as possible because the whole point of the NSF grant that was given to OSHA was to promote such devices. So I mean, they said that they'd be really excited and really happy to collaborate and certify this.
Yeah, I think I remember before we started this project, actually, we had done an interview with a couple people from OSHA, and it was essentially us giving feedback on what we think should be a more certifiable framework on what open sourced hardware or medical devices look like. And it was this ongoing debate because, as we're saying, I think medical devices need more reliability and validation, but you can only get that validation once you've completed the device, right? But then part of the ethos of open source is, hey, maybe you get 75% there, you put it online, and then someone else takes it forward. And so we were having this giant debate as to, is validation one of the things that require in order to be certified? Like how does that kind of start veering into, like a research paper publication style? Is that too high of a barrier to entry to get people to do a medical device? And so we were just having this giant debate into what a proper framework for an open source medical device looks like. So, open-ended question for the audience to think about, for everyone to think about, what do you really need to certify a reliable open source medical device?
Yeah, for medical, you would want some kind of validation, because if you're putting out the design out there and someone builds it and it doesn't do what it's supposed to do, even though it's an open source license and it could be built, they're still not getting what they expect.
Exactly. And we, I think, had some other problems too. We were saying, when we were building this wire prong, originally we were thinking of creating this like giant wire bending jig. When we were, going to screw some things in and then it would wire automatically with a feed machine. But then we were thinking, and we're like, well, how many people are going to have this complex wire bending jig that the resources of Cornell do? And so we ended up just buying jewelry pliers on Amazon, and we were like, okay, we'll just hand wire it, hand bend it. But then in that process, we were like, how can we communicate across the screen that this is exactly the dimensions that they need to do it at? And so I literally ended up tracing the shape of the wire on a piece of paper and then putting like a quarter next to it, took a photo, and I was like, okay, everyone, print this out, zoom into your photo to size, and this is how you're going to bend your wire. And so it was trying to assess the accuracy, but also balance the scrappiness of what open source ethos is.
Key part here is the way we convinced the surgeons and the doctors to come work with us was because we wanted to keep them and place them on the driving seat and draw the device around their use. I think that was really important. And a lot of times, medical equipment that are being designed are really they're far apart from what's the actual use case. Sometimes I think that's something that we can focus on.
Michelle, any thoughts as we wrap up?
There were other things that we also had to do, including like the 3D printing, the like form factor prototyping as well. I think one thing elaborating into that tension of scrappiness versus medical grade hardware, we were literally just building in the maker lab. Like we were quite literally, just scrapping it up in the maker lab. And so all of our prototypes for the physical, like the handheld portion encasing the hardware, it was all 3D printed. And honestly, it had like a lot of bumps and I tried to sand it out, but it just kept making it worse and worse because the dust was getting everywhere and into the crevices. And so highlighting that tension, again, we were like, how will a patient feel if their doctor's holding a little 3D printed screwdriver toy? And then we're like, how will this hold up over the years? And that was one of the issues and the tensions we had faced as well. So I think as a clinician right now is using it, we're excited to get feedback. And perhaps we will have more resourcing to cast it better or, wrap it up in silicone. But I think our first version was definitely perhaps not built to last, to say the least. And I think adding on to that tension as well, me and Reitwiec are both in grad school and this is our final year here. And so we are wondering about the open source maintenance of a medical device as well. And we were wondering like who will carry this forward? The clinician and they're not necessarily the most technical people in terms of being able to install the software breaks. And so one of the kind of lasting questions in the back of our head is, how is this going to go forward? And that was originally one of the issues with the original proprietary medical device, was that they were being charged every single year essentially to have some sort of maintenance certification. But we realized the certification didn't actually do anything. Like the device was so simple in terms of load cell and the calibration. All you have to do in order to calibrate it is hang a weight on it. And that will be your reference point. And once you reference point it, it'll just reset the calibration. It was so simple. I was like, no one needs to be charged for this. This device is not going to be sent in to maintained every single year. But in the back of my mind is, what are we going to do? How are we going to communicate to this clinician? How are we going to validate that there has been no measurement drift across time? And so that has been one of our longstanding questions of open source as well, especially in the medical use case.
Yeah, that's a great question. And I know I don't have any answers off the top of my head for that.
At least talking about the wear and tear, one good thing about open sourcing this is, even if it wears down, you can just reprint it. That's like the part about this. Like the main core part still stays. They can just reprint the whole outer casing if they want to, with different colors. Honestly, if they want to use it on different age groups of patients, they can make it cuter if they want to do it. So there's endless possibilities in terms of making the device look approachable and safe.
What's next for you with the device?
I think what's next right now is, as we mentioned, because it's a medical device, we really invested into making really extensive documentation. As I mentioned, even drawing out how the wire should be bent. For example, we had to like drill a hole into our load cell. And I was like, how do I map out and communicate to someone where to drill this hole and like how deep the hole should be and all of these things. And so we really invested a lot of energy into making very extensive documentation. So we're hoping to get like a V1, V2 out soon. Other things that are next is obviously iterating clinician feedback. Other things is also building that framework out with OSHWA, so scaling the impact. And we're also interested in perhaps some sort of publishing commentary that we're working on to, I guess, propose this new framework, as we're saying, of how open source has enabled participatory medtech development in contrast to what industry proprietary black box looks like. It's you build the device and you put it and you sell it to hospitals that are super expensive. I'm highly dubious that there's any sort of clinician iteration loop that's happening there. And so we really wanted to publish on what a new framework could look like.
Yeah, and we're also waiting to hear back from the PI because I think he was planning on using this as part of his research as well as he uses it on patients. So we're looking forward to his findings and his results and how that goes. Yeah, super exciting.
That is exciting. Reitwiec and Michelle, thanks so much for coming on the show.
Yeah, thank you so much for having us. It was really fun chatting about all this.
Thank you for listening to the CircuitPython Show. For show notes and transcript, visit www.circuitpythonshow.com. Until next time, stay positive.